Hi, I'm MAE0086 and I'm the team lead for the Modular CubeSat project at UCI. First off, what is a CubeSat? So the CubeSat was a satellite standard created in 1999 by Cal Poly School in Stanford, and it consists of units of 10 centimeter by 10 centimeter by 10 centimeter cubes, each one weighing 1.33 kilograms. What's very great about them is that they're very low cost, and a lot of them use just off-the-shelf components you can buy in a normal store. And the low cost also is attributed to being secondary payloads to larger missions, such as SMAP or any of the Falcon 9 rockets. So the Modular CubeSat project stemmed from an idea from the NASA PhoneSat. So this was one of the biggest innovations in CubeSats back in 2013 when they used a smartphone to power the whole satellite. And the whole cost of the satellite ended up being $3,500, which was really cheap compared to the $100,000 CubeSats that were being made at the time. So the Modular CubeSat main goal is to build UCI's first satellite. We've had 3 projects in the past, but due to various reasons, they never completed. And we want to also improve upon the PhoneSat and allow for a simple satellite system to allow anyone to build a satellite. The modular development style will allow anyone without any coding to build a satellite. It's a 2U satellite, as you can see, so there's 2 cubes on top of each other. And the idea is to use it as a proof of concept. And we're using tape measure antennas in order to minimize costs. We're using the amateur radio band, which gives us a wider range of receivers and transmitters we can use. And everything is off the shelf. Everything from the frame to the transmitter to the cell phone, all off the shelf. You can buy it at a store. And the idea is for it lasts a week in space, battery-wise. We don't have solar panels. And then NASA provides free launches for schools, which also minimizes our cost by a large amount. And the idea is why we're using the Moto Z smartphone instead of any other smartphone. It is modular. So it allows anyone to build an instrument. It's Raspberry Pi based. So anyone who can code for a Raspberry Pi can build a scientific instrument for the satellite. And for our concept, we're going to be using a temperature sensor as a proof of concept. In order to help us with our design, there's actually CubeSat specification. It covers mechanical, electrical, operational, and testing. On the mechanical side, it's dimension requirements. Everything has to be within 0.1 millimeters on the outside. Electrical, they limit when you can turn on and off the satellite. Operational, the FCC requires when you can transmit and receive. And it also has to survive the launch, so vibration, thermal, and shock testing. So currently, we're able to do communication between a smartphone and a computer using amateur radio. We're able to transmit data. We analyze our antennas using ANSYS HFSS. And we were able to transmit back and forth and send signals and control the smartphone through there. Now, just recently, we actually got a software-defined radio, so we were able to extend our communication skills by a larger amount, and that also allows for Doppler shift. So as the satellite goes around the Earth, there is a Doppler shift in its radio frequency, which we do have to take into account. Thermal-wise, so CNR Technologies was kind enough to offer them our thermal software, a thermal desktop, and we were able to actually do thermal analysis on the whole satellite. And we did find out that it is in between -30 to 46 degrees Celsius. On the high end, that is perfectly fine for the satellite. On the low end, we are kind of worried about the phone not turning on and the battery life being very low. So we're going to be optimizing the location of all the components so they keep each other up and keep a higher temperature. This was last quarter. We were able to do a very basic prototype because we did not have the frame yet. And we were able to test the deployments of the 2 antennas and went through all of the launch sequences. So after 30 minutes, it would do this, it would deploy the antennas. After 20 minutes after that, it would transmit. And it passed perfectly. This was more of a software test. And everything worked very good. It was a very good step for us to move on. Now, a few weeks ago, the prototyping frame was created. It is assembled exactly how the final frame is actually assembled. So the frame we will buy from Pumpkin company called Pumpkin. It was developed in this way to handle loads. So the closer we can match the final product, the better we'll be able to assemble once we get all of the final components. The biggest part that happened to us was that we actually we applied for a competition in December. Lenovo started a competition saying, who can build the best module for our smartphone. And we actually became a finalist in that competition at the beginning of February. And we can now move on. And the end of the competition is that if we do get enough funding they want us to start an Indiegogo account, an Indiegogo fund. If we do well enough, we'll go to Lenovo Capital and present our idea to Lenovo, and they can fully fund. We have a potential for fully funding the project. So we received the full smartphone development kit, and we are going to be starting our Indiegogo campaign in the next few weeks. And our budget, so our budget total is up to $4,000 per satellite, with the total cost of the project being close to $8,000 to $7,000. Because we're building 2 satellites, one for testing, one for the final design. And our timeline, we're going to be having a working prototype at Winter Design Review to show off. Our electrical components are being completed this week and going to be assembled in the frame this weekend. We are a multidisciplinary project. We have people from computer science, EECS, and MAE. And our advisor is Professor Reese. Any questions?